Alrighty, good morning, everybody. We're gonna actually let me copy the thing over from last time. Let's see. I'm gonna copy our little chart over just so I can reference it because we're gonna start doing much the same stuff that we did last time. Alright, let's see here. Let's get all this good stuff. Alrighty, and let's start our new one. Much the same way. Okay. So now we'll have this for our reference. So just remember, what we're really doing this chapter is just applying these reaction coefficients that we dealt with when we were balancing equations. With them, we did a couple of examples all over the place. Let's start with one now. Let's say we have this reaction. Well, this is not one that can happen, but hold on. One of the dogs, I think, is in the recycling bin right now. Alright, one moment. In the meantime, take a look at this and see if you can balance it. And tell me what type it is also. Indeed, this one was stuck in the recycling bin. How the heck did you even get in there, mister? Crazy doggy. So, hopefully you've balanced this by now. You should see that you have those. Let's throw some state symbols on these. This is, of course, a single replacement type reaction, in case you have forgotten that. Please don't. Your exam is in a week, so make sure you definitely do not forget that. Alrighty, so let's say that we have... this amount of sodium chloride reacted. What pressure of Cl2 is produced in a 2-liter container at 250 Kelvin. Let's just make that 3 sig there. And let's say they say that I'm looking for atmospheres for this. So, as always, we want to dissect our problem. So, it looks like we have some conditions starting for sodium chloride. We're asked for a pressure at the end. We know that the chlorine is a gas. We, of course, then have our other components for the gas there that we can see. As always, we want to do our plan. We know the moles of sodium chloride, or rather we can know them. That's the information we're given. We know that we need to go to moles of chlorine. Remember, this is our reaction coefficient that we're going to use there. And now we want to take a look at what we're given to start with and what we're looking for here. So with the moles of chlorine, we're asked for pressure of chlorine, which we can do, or atmospheres, we can say, since we're just putting the units out. We can do that, right? We have the relationship between that. Right, we can use our ideal gas law to go from moles to atmospheres of a gas. I could have asked for volume too. or temperature. Remember, I could ask for any of those. Nothing different there. If we want moles of sodium chloride, well, what we're given in the problem is a molarity, right? Molarity is a conversion factor between moles and liters of solution. So we know we can get moles by using the liters. And of course, since we're given milliliters to start, we'll need to just quickly convert that as well. That's just a plain old metric conversion. And here was our molarity. So remember, there's only really 3 conversions we can do. We can use molar mass to go between mass and moles. We can use molarity to go between volume of solution and moles. And then we can use our ideal gas law. And that's really the only 3 conversions that we're going to be dealing with here. So it's going to be kind of your job to remember which one to use when. So that's what this whole chart is for. So you're only ever going to use molar mass if you're dealing with grams. In this case, we're going from, we're here with volume of solution, and we're ending up with our gas stuff. So by looking at this chart, we see we're going to need the molarity of A, which is sodium chloride in this case, and then we're going to need our ideal gas law for the second one, for the ending conversion there. See, so nowhere in this do we use molar mass. Molar mass is only if we use grams. And so in this particular problem, we're not using grams, so there's no need for any conversion factors except the ones that we've kind of circled here as we've gone through it. So this is definitely a handy chart to have at your side. So it'll tell you kind of which conversions that you're going to need based on what units you're looking at. So let's go ahead and take a look at this. So we're going to start off with our 32.6 milliliters. We want to first convert that to liters. Of course, you can do that in your head if you like. We're going to use our molarity, which was 0.750 moles for 1 liter. And we'll be good and include our substance with this part. We're going to have our reaction coefficients, which are 2 and 1. And then we have our... let's just end up at moles of Cl2 so we can use our formula here. So let's just do this part for now. If you want, you can go ahead and do it all at once. That's not a problem. But let's just go from here because I'm out of space anyway. So 32.6 divided by 1,000 times 0.75 divided by 2. Doing this, we get 0.012225 moles of chlorine. Our ideal gas law, PV equals nRT. Since we're solving for pressure this time, it's nRT over V. So we can say that the pressure is 0.01225 moles times 0.08206. And then we have our temperature all over our liters, our volume. And so we can do this times 0.08206 times 250 divided by 2. Oz is, of course, being naughty outside now that he's out of the garbage can. He's now outside borking, but I guess now he's stopped, so we're good. And we have our answer. You can just go ahead and, if you wanted to, continue this from here. If you wanted to just do it all in one spot, right now you have moles at this point in the unit conversion. You can just multiply it by RT over V, and you would get your pressure out directly without having to stop in the middle. It's up to you. You could have just done it this way with this blue thing, and that would get you out your pressure as well. Since we know that this is the conversion we have here. Oh, sweetheart, relax. So you can just throw that in there if you want. Alright, so notice again, no molar mass here. That's kind of the biggest mistake that I see semester after semester is students will just say, I need to use the molar mass somewhere. And there's really no reason to do that if you don't have grams anywhere in your problem. If you're not given grams, you're not looking for grams, you do not need the molar mass. Another thing that I see pretty commonly. Here, let's do it. No, let me do a different problem. Another common mistake I see is using coefficients with the molar mass. That's something that I've seen a lot as well that is not necessary. So let's say we have all right. So here's one. What volume of oxygen is required to produce 50 grams of water if the pressure is 1.28 atm and the temperature is, let's just say, 380 Kelvin. So, start, as always, with your reaction coefficients in the middle. If we look what we want, we're asked for grams of water. We can go from moles to grams. What we're given to start with is volume of O2. We know O2 is a gas. So we're looking for... Oh, I'm sorry. We're actually going to be doing this the opposite way. We have our grams of water that we already know. We're kind of working backwards here. Okay, so I've just reversed all that stuff. And now we're asked for volume. So we want to figure that out there at the end. We, of course, have our reaction coefficients. We have our ideal gas law. And here we have the molar mass of the water that we're going to be using. Of course, if we look on our chart, this is what we're doing. This time we're going directly diagonal. So we're going from grams of water to moles of water to moles of oxygen to, in this case, volume of oxygen. That's a gas. All right, so we're kind of going through this middle pathway. All right, so looking at the problem, we have 50 grams of water. What some people will do is they will say, okay, well, we have 2 waters, so that means the molar mass is 36.04. That's never the case. Molar mass is going to be a constant. Just so you remember, molar mass does not include reaction coefficient. It does not matter how many waters you have in your reaction. Water's molar mass is always, 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 always 18.02. No exceptions. Once we have our moles of water, we can apply our reaction coefficient. And then we have our 1 mole of oxygen gas. And let's just go ahead and do this one all together. So we're going to end up with moles, so we need to put RT over P. Or if you like, you can go ahead and pause here and then plug it into the formula if you prefer that way. And then our pressure was 1.28. Oh, I forgot the units here. All right, so grams will cancel. Moles of water cancels. Moles of oxygen will cancel here with R. We've got kelvins canceling out with the Kelvin here. Atmospheres, we're going to be left with liters. That's what we want. And so let's go ahead and take a look at this. So 50 divided by 18.02 divided by 2 times 0.08206 times 380 divided by 1.28. And we get out of here 33.8 liters of oxygen gas. So we're going to need that much to make that much water. So we're just kind of taking our product there and figuring out how much reactant we need to make it. All right, so this is kind of the whole idea again. We're just looking at this chart, figuring out what we have, figuring out what we want, and just applying the unit conversion process to get us there. So we're going to see that that's kind of the main idea of this chapter. And so, any questions on that one or the one before it, by the way? So, again, you can go all over the place. It just depends what you're given and what you're asked for. So you can go all over. All right, and you always want to start with whatever you have enough information to get moles of. Right, that'll be your, like, A. And then B will be the mystery one. Okay? Alrighty, well, so far we've just kind of been looking at one pair of things at a time, right? We've been saying, okay, how much oxygen do I need to make this water? How much chlorine do I get out by reacting this amount of sodium chloride? We're going to see that sometimes we have an idea called a limiting reactant. So if we go back to our sandwich from last time. Remember we had 2 bread pieces and 3 lettuce and 1 tomato equals 1 sandwich or something like that. That was our reaction. So let's say if I have 6 bread, 22 lettuce, and I don't know, pie tomato. And let's say pie. Let's just be good. 4 tomatoes. 4 tomato. How many sandwiches can I make? So last time we were looking, okay, well, if I have 6 bread, well, I know how many sandwiches I could make with that. And if I have 22 pieces of lettuce, I know how many sandwiches I can make with that. And the same thing with the tomato, right? But now we're going to want to look at them all at once. And so what we're going to do is just apply our stoichiometry for each reactant. So we're just going to be doing the same process 3 times here. Let's just go ahead and take a look at what that's going to look like, and then we'll go ahead and apply it to chemistry. So let's go ahead and look at the bread. So I have 2 breads. Oh, I'm sorry, I have 6 breads. That's what the problem says. And I know that I need 2 bread to make 1 sandwich. And so from this, I can make 3 sandwiches. Hooray. I have 22 pieces of lettuce. I know that I can make 1 sandwich for 3 pieces of lettuce. And so that's 7.3 sandwiches. And lastly, I have 4 pieces of tomato. We know that we need 1 tomato per sandwich, so overall we can make 4 sandwiches. And right, so now that we've kind of looked at all of these, hopefully we can see that in reality, if we are going to be making our sandwiches, only one of these numbers will be kind of applicable to us. And hopefully we can see that that's going to be our answer there. We will run out of bread after making 3 sandwiches. Therefore, bread limits the amount we can produce. And as a result, we can say also the lettuce and tomato are excess. All right, so we have extra of those. No matter how much more lettuce we have, we can't make any more. So, in chemistry, oftentimes you will have an ingredient that will run out before the other one, or other ones, if there's more than 2 reactants. And so you'll see that one of them will limit the amount that you can make. And so we're going to see that the amount you make is always going to be the smallest number you get out of it. The amount that you can make, which is what we're going to call, by the way, the theoretical yield, is the smallest amount that a single reactant can make. And so we're going to see what this looks like with some examples. So it's really, we're just going to have to do this multiple times now for each reaction instead of just doing it once. So let's take a look at some examples here. And we'll just use some we'll start off easy. We'll just do the mole stuff, and then we'll go from there. If I have 3 moles of, I guess I should give us a reaction. This is Very common reaction for us. In 113, we study this reaction like in every chapter. It's awful. They have their exam today, by the way. Of course, I've thrown this equation back at them for the like 800th time. So we can do this for them as well. So, anytime that you're given information about multiple reactants, you have to take, hello Anne, we have to, oh, that's okay. If you missed anything, you can kind of backtrack. You can go back in time to take a look. And so that'll let you do that. Unless there's like a question you have. But what you want to look at this is now we have to have two plans. Because we're going to be doing two dimensional analysis, two unit conversions. And since I've made this super easy for us, we just have the one conversion, which are our reaction coefficients. And so we're going to have to just do two unit conversions. So we had 3 moles of nitrogen. We have a coefficient of 1 there. And they can coefficient of 2 there. So we could make 6 moles of ammonia. With our hydrogen, we're going to do a separate one. And here we get, let's see, 10/3 is 3.3. Alrighty, and so what you want to do is you're always going to choose the smallest one. So we can make a maximum and we can also say that hydrogen is what's called the limiting reactant. And we can say N2 is excess. We could say that as well. So sometimes I'll ask, what's the limiting reactant? What's the excess reactant? What is your theoretical yield? So that's another way of saying this. So theoretical yield, which is again the maximum amount you could make, will be 3.33 moles of ammonia. I guess I've kind of thrown sig figs out the window here, so let's just fix these. There, now we're happy. There. So now we have 3 with more than 1 sig fig. Alright, so we will end up making only 3.33 moles of ammonia out of this. So whenever you're dealing with something that has multiple reactants, or are given information about multiple reactants, you have to do it for every single reactant you have to figure out which one is going to slow you down. So let's take a look at another example here. Let's say we have let's do something with okay. Here, I'll make this a little bit easier. It's mixed with what mass of so we're given our reaction here. We have calcium chloride reacting with sodium carbonate. We end up with calcium carbonate, of course, and 2 sodium chloride. I know I'm zipping through the reaction part here, but hopefully by now balancing something like this is not too bad. We know we have 2 reactants. And we have information about both of them. And we're asked for one of our products, a mass of it. So, because we have information about both reactants, we have to do the unit conversion process twice. All right. So, with this, let's just go ahead and take a look one at a time. So let's just do for the calcium chloride first. We know we're going from moles of calcium chloride to moles of calcium carbonate. The question is asking us for mass, so we're going to want grams of calcium carbonate at the end. And we see that in the problem we're given liters and a unit conversion to get us from liters to moles. So let's see what those are going to be. Of course, in the middle are our reaction coefficients. To go from liters of solution to moles is, of course, molarity, which we're given in the problem. And then to go from moles to grams, we would, of course, use the molar mass. So, again, if you can set up your plan, you can figure out what conversion factors you'll need. After that, you just plug it in as you go. So we start with our liters, 0.220. We're going to use the molarity, 1.25 moles per liter. This is calcium chloride. Next, we're going to use our reaction coefficients, which were both 1. And then we have the molar mass, which I'm going to just look up right now. Molar mass of this is, wow, it's almost exactly 100. Okay, so 100 point, let's say 0.9, we'll say. Doing the math, we get 0.22 times 1.25 times 100.09. We end up with 27.52 grams here. If we take a look at the second one, in this case, we're going to have much the same. This time we're using sodium carbonate to get to calcium carbonate. And then finally 2 grams of calcium carbonate. And we're starting with liters as we did before, because that's what we're given in the problem. I could have given you mass instead, or I guess I couldn't have given you gas because this is not a gas, but I could have given you other stuff. So it's not always going to be exactly the same process for each reactant. But since it is in this case, all of our conversion factors are the same. So let's do it. In this case, we have 1.160 liters. 2 moles per liter. We are given our reaction coefficients. In this case, they are again 1. Doing all this fun stuff. Let's bust out our calculators. Doing this, we get 32.029 grams. Now comparing our numbers, we always choose the smallest one. And so our answer is, we're going to say 27.5 grams of calcium can be produced. So we are going to have extra sodium carbonate floating around in that solution. We're going to use up our calcium carbonate. I'm sorry, our calcium chloride. Making all this calcium carbonate. All right. And just so you know, this is another way to say this is the theoretical yield is 27.5 grams. So it's exactly the same way of saying this sort of thing. Alrighty. Let's do another one. Let's see here. What else can we do? What's a good reaction for us? Yeah, let's do something like this. I'll balance it for us. All right. So let's just say that we have this reaction here. I'm giving you the state symbols because they're a little bit unusual. Let's say I mix 10 grams of aluminum with 0.30 atmospheres of chlorine at 298 Kelvin and 10 liters. What molarity of aluminum chloride is would be produced if the final solution volume is half a liter. Okay, let's go from there. Alrighty. Let's take a look at this problem now. So let's take a look here. We have our first reactant, and we have enough information about that reactant to get moles. We have our second reactant. We have enough information to get moles from that. And we're asked for molarity this time. So we're probably going to want to stop at moles, and then we're going to just divide by our 0.500 liters at the end here. So let's take a look at what this is going to look like. So if we look at our first set of stuff, we're going from moles of aluminum to moles of AlCl3. We are going to want to divide that number. Well, let's stay with moles of AlCl3 for now. All right, and we're starting with grams of aluminum. So we'll work with this in a little bit. That's kind of our first one. So the reason that we're going to stop at moles, remember that molarity equals moles per liter. So we have our 0.5 liters here. So we just need to get the moles first, and then we can just divide those once we figured out the moles. For our second one, we're given gas stuff for chlorine. Which we can then convert. And then both of those numbers we can plug into our molarity. So let's go ahead and see what the conversion factors are going to be. We have the molar mass here. We have our reaction coefficients. Here we have our ideal gas law and our reaction coefficients. And then later we'll use the molarity, or we'll figure out the molarity by doing our moles divided by our liters. So for number one, we're taking our 10 grams of aluminum. I need to look up its molar mass. Aluminum has an atomic mass of, what is your atomic mass? 26.98, okay. And then we know we need 2 moles of aluminum for 2 moles of AlCl3. We can get our answer, so 10 divided by 26.98. Except I don't know how to divide 26.98. All right, so I get 0.3706 moles. Our second one, we had all this fun stuff. So N is PV over RT, right? So we've got to plug all this in. So we've got PV up top. 10 liters. 0.08206. Was it 298 Kelvin? Oops. Oh no. 298 Kelvin, yeah. So that'll be moles. We've got our reaction coefficients there. So let's do this. 0.3 times 10 divided by 0.08206 divided by 298 times 2/3. From this reaction, we get 0.0818 moles. Already we can see that the second one is our limiting reactant, the chlorine, but we technically have only solved for moles. If you really want, you can do the molarity of each one and you'll see that it'll still be for number 2 there. If we end up getting the molarity, we know that molarity is moles per liter. We had a solution volume of 0.5 given in the question. So if we do this, we end up with 0.164 moles per liter. Or just leave it as capital M. And that'll be our answer there. All right, so the whole point today is that when we're given multiple reactants, we have to do this process for each one. And we choose the smallest number either as our answer or to move forward if there's one more step. Like this one had one more step at the end to find the molarity. So we could stop at moles and say, okay, the moles, we see that the second moles are much smaller than the first moles. So obviously it's going to give us a smaller molarity. We always want the smaller one for this sort of thing. And so in this case, chlorine was our limiting reactant. Aluminum is our excess reactant. And we'll end up producing 0.164 molar solution at the end of this reaction. All right. So just adding more steps. That's all we're doing here. Again, not really new stuff necessarily. It's just taking it in one more step further. I don't want to go further today. We just have one more kind of part of this chapter left to go. We'll just go ahead and do it tomorrow. It's when we have reality coming in to mess with our reactions. So we'll talk about yields tomorrow. But I think I want to stop here today because this is a lot of math. I get it. A lot of things going on. I think it'd be a good idea to kind of let your brains rest a little bit. And then we'll just pick this up tomorrow. We'll finish it up and then we can start chapter 11, which is our last chapter. So everything, including everything from 9 and 10, including what we do tomorrow, will be on your exam next week. So Thursday, if you want, we can do our review. The stuff for chapter 11 that we learned will not be on your exam next week. So if you want, you can just not watch those videos and watch them after your exam or something. So whatever you like. So, all right. So with that, I'll see you tomorrow. We'll finish this off and enjoy resting your brains. So see you tomorrow.